So today we're going to be talking about recursion. So what is recursion? Recursion is when a function, so let's say a function, let's call this a function func, and let's say it takes n, and n is defined as some integer. And let's make this the function definition. So this is declaring what this function is. And we're going to go ahead and print n. We're going to go ahead and print n. What is this number? What is this number? And then we're going to call this function definition again with this time n minus 1. So what's going to go through? It's going to go through this function. It's going to give us our prints. And it's going to call this func again, go back to the top, and keep printing this n. So what does this look like to the coder? What is the coder's sort of point of view of this? So the coder is going to put func, it's going to call this function, say func5. I'm going to call this function func5. And then the terminal is going to output, we start at, so we said 5, so the first time we're going in, we're saying 5. It's going to go down, it sees the print statement, it's going to print 5. And it's like, well, let me run this again, but with n minus 1. So it goes through again, this time 4, and it does the same thing. Now it's going to keep doing the same thing over and over and over again till infinity, because we don't really have a stopping condition. There's no stopping condition here. Now, what does this look like? What does this look like to the computer? What does this look like to the computer? The computer keeps track of a stack. And the way a stack works is it's first in, last out. So think of plates we're stacking up, And we're going to wash these. These are plates we're going to wash. And the first plate we put in is going to be the last plate we clean. So we look at the top of our dishes to clean. We clean this dish, and we work our way all the way to the bottom to the last dish we have. That is essentially what a stack is, and our computer uses this to sort of keep track of what functions we visited or what functions we need to go back to after we've done it. So say our first function call here is func5. Then it goes through, it's going to go through this function, it's going to see our print, it's going to print the 5, it's going to print this 5, and it's going to say, whoa, hold up. There's another function call. So before I continue looking at the rest of this sort of function, I need to, dive deep into what this n minus 1 is. So we do func n minus 1, which is 4. Then we're going to see the print statement, and we're going to keep adding this on and on and on. This is useful for things like, what if we needed some sort of sorting step at this stage, or we need to run some sort of subroutine. This allows us, after it's finished, the idea is that this gets popped out, and then we can start back evaluating the rest of this function over here. But now we don't really have a stopping condition for this. How can we add a stopping condition? The stopping condition is usually called the base case. Now, how can we add something like that? Well, we need to look for a condition to stop our sort of function. Let's stop our function here at this 2. So when n is equal to 2, just return. Stop what you're doing. Stop this nonsense. Let's just return. So if n, so let's use the same color. If n is equal, so double equal signs is equality. Is equal to 2, I want you to return. Return. Now what this is going to do, it's going to go down. It's going to say, okay, we're at 4, and 3, then n equals 2. Once we get to n equals 2, it's going to go down, and it's going to say, okay, n is equal to 2, return. We're not going to get this print statement over here because we've already returned, so the rest of this function is not going to evaluate. So this 2 doesn't happen over here, and this negative 100 doesn't happen. What does this look like to the stack? So we're going to see func we're going to see func2. We're going to make this call in the first place. We're going to make this call. It's going to come in and it's going to read, oh wait, n is equal to 2, so let's return. So we're going to follow this return statement. This is going to return. In turn, this is going to pop off the stack. So we returned, so we're finished with this 2, so it returned. Now this function 3, from the perspective of 3, so think this definition now is sort of the POV of 3. So 3 here. 3 here is looking, and it's like, wait a minute. We just got a return statement that came out of here. So we just returned from this n-1, which was originally the 2 call. And we came out and, well, there's nothing really to do. Our place was saved here at 3, so our place was just sort of stuck. We were stuck pointing sort of at this line. We were waiting and pointing. We were waiting like, okay, when are you going to come back to us? And it's like, okay, we got the return. What else is to evaluate? Well, there's nothing really underneath this function. There's nothing else to evaluate. So since there's nothing else to evaluate, this function is going to be like, all right, I'm done. And so forth, all right, I'm done. All right, I'm done. And then all our items are getting popped off the stack one by one. This is how the base case sort of clears up our stack history and allows us to perform recursion and stop it at a designated point. Say you were given this problem. And you were told to evaluate mystery 4 and 3. And you're told to evaluate 4 and 3. What would you do? First thing you can do is just, first off, look at what we're getting in. So we're getting n, we're getting a. What's happening here? Okay, so we see that our base case seems to be that when n is equal to 1, we're just returning a. And then every time we multiply a with the returned statement of this mystery call. So this mystery call is going to be digging deep somewhere, and it's going to eventually pop back up and multiply with a. So instead of trying to do this sort of in our heads, let's think like the computer. And open up a stack. Let's open up a stack and sort of draw this out and work with it. So this is our stack. And we know our first call to this is going to be 4, 3. You know our mystery call is going to start out with 4, 3. And we're going to work our way down, and we say, okay, n is not equal to 1 here. So we're going to multiply a. So what in this case, what is a in this case? A is 3. So we're going to multiply 3 here. So there's going to be multiplied with something, the return statement, but we don't have anything to return at this moment. So let's just sort of move on to the next call. So we do n-1, so n in this case is this 4, so we're going to do 3. Let me see, okay, well, n is not equal to 1 yet. So we're going to keep going. We're going to keep following this pattern. 3, and then 1. So we finally reached n is equal to 1. So what happens now? It wants us to return a. So we're going to end up returning a. What have we been doing this entire time? We've been waiting 3 times on this one and 3 times. We've just been waiting right here with this 3 times. And now we're finally going to get our first return statement. And it's going to say return a. So it's going to return 3 here. So 3 is going to be returned. What's 3 times 3? So it's going to evaluate right here. Finally, we're going to get 3 times 3. And that's going to return this. So we're going to get 3 times 3, okay. We're going to get a return statement, so it's going to be 9. 3 times 9, we're going to get a return statement, 27. 3 times 27, we're going to get a return statement, 81. And the answer to this question is indeed 81, and that is how, if you were given this, how you would solve it. Let's try another one. Now we're going to get a little bit more abstract here. So looking at this function, how would you trace mystery 6 and 2? 6 and 2. So this is a lot to look at. This is genuinely a lot to look at. So if you were given this on a test, do not panic. As long as you write out the stack and you trace it all the way through, you should be fine. So let's start out with n and a. So what is n and a? Let's define n and a to be, some integers. So these guys are just some integers. And we can see that by definition. So let's go through and analyze this. So we see that our base case here is when n here is equal to 0. So let's examine, okay, how is n being decremented then? So we see n minus 1, n minus 1. So we can assume that as we go up, we're sort of going to see a linear decrease in sort of this n here, And now what happens when we get to here? This statement is saying n mod 2 is equal to 0. So this is saying when n divided by 2 is something, some x, the remainder is 0. So that means that n is evenly divisible by 2. So we're going to see when n is divisible by 2, run this statement. So anytime we look at our n over here, our incoming n, when our incoming n is 2, we are going to run this sort of mystery statement. And then finally, if it isn't divisible by 2, we run this statement where we add 1 and wait for our return to add it with this sort of return statement. So we have one return statement without adding and one return with. So you can go ahead and pause the video if you like and sort of try to work this out yourself, and we'll go through it together in just a moment. Okay, so we know our first call. So let's do this. We know our first call is 6 and 2. We know our first call is 6 and 2. And we go through, so we're going to say 6 and 2. So we're going to go down and we're going to say, okay, n is not 0. And we go down and we say, well, 6 is divisible by 2. 6 is divisible by 2. So we're going to call this statement. So we're going to make this call. We're going to call this statement, and the statement is going to be n minus 1, so 5, and then a plus 1, so a plus 1, so it's going to be 3. And then we're going to evaluate sort of 5 and 3. So if we had 5 and 3 here, 5 is not equal to 0, 5 isn't divisible by 2, so we're going to be running this statement. And this statement says 1 plus the returned statement, so 1 plus whatever's returning over here, 1 plus whatever we get from this sort of mystery call. And we see that this call is going to give us still 4 once we decrement by 1, and we're going to multiply a by 2. A here is 3 in this case, so we're going to get 6. We're going to get 6 here. And now let's just follow this all the way through. We see that, okay, it's divisible, so we're just going to decrease and increment by 1. This is odd, so our next call is going to be this 1. So we're going to do 1. We're going to do 1 plus some mystery statement that's yet to return. And the odd call is going to multiply the a. So we're going to get 14 multiplied by 2, and we're going to decrement. And then again, if we can see the pattern here, we're just going to increment by 1, Since it's negative, not negative, since it's odd, we do 1 plus again, and our next call is going to double. So 30 and 0. Now n here is equal to 0. It's saying to return a, so it wants us to return a. So let's go ahead and do that. So we're going to return 30, and we're going to return 1 plus 30, which is 31. This statement is going to say, okay, we didn't really do anything, just return me. Return, and we're going to do 31 plus 1, which is going to be 32, and then it's going to return, and it's going to say 32 plus 1, and it's going to say 33. And that is our answer. 33. 33 is equal to 33. Now this next example is going to be about binary trees. We'll go through how this looks like. We've made a previous video on the orders and what these orders represent and mean and how we process these. But for now, we're just going to use this as just a small exercise. If you're interested, you can go check that video out, but it's not completely necessary to understand what we're doing. So say we have A, B, and C. So in a data structure in a hash table, this is going to be represented by, let's say, A, B, C. And these entries are going to be left and right entries. So left, right, left, right, left, right. So A has a left B and a right C. B has nothing, so we're going to put like null. It's null, and null, and then null, then null. Now, the question is, given this graph here, given this tree, let's call it sort of T. Given this T, so this is T, what would be printed out to the console? As a reminder, so we are inputting tree, so we have the tree, so it's this structure right here. We have that tree, and then what we're going to do is we're going to access the left and right nodes. So here, if we wanted to get B, if we wanted to return B, the way we'd notate that would be T, and we say grab us the A entry, and give us the left entry 0. This is indexed 0, then 1, 0, then 1, 0, then 1. And if we grabbed this entry T, and we said C 1, so this would be equal to, this is equal to over here B, so equal to B, and C would be equal to null. So it would be, or in our case, what we're going to see is going to be none. So there's nothing there. It's none. So how are we going to evaluate this function up here? So let's look at it. So we have two function calls right next to each other. So we're going to be evaluating this sort of binary tree traversal. And so we're going to go through. So we're given a node. Let's say our starting node is binary traversal. I'm just going to cut it short, traversal, and it's going to be the tree, and it's going to be A. Say A is our starting node. The best way to traverse if you're given sort of graph problems, you can use the stack, but it might be helpful to use the actual graph itself. So if we start out at A, so if we input A is not null or nothing, so we continue, and then we reach the statement print. So we're just going to, so let's say our console down here, so we're print, so what are we printing? We first print A, and then looks like we go down to the left. So we now go down to the left, and now since we're at the left one, we're back at B, and B is not nothing. It's going to hit this statement. So okay, so it's going to say B, and then it's going to traverse left again. Now this time, what we get from the B is this right here is nothing. This is going to return none, so there's nothing there. So we're just going to return back to B. And where we left off from B is that we left off going left. Now we're finished with this statement. Now we just have this right statement to evaluate. So now we're gonna, from B, we're gonna go to the right. And after we go to the right, there's nothing again, so we return. And after we return, we're finished with these two statements. And the only statement left is this print. so we print B. Now, you can pause the video to see if you can get how this print statement is actually going to unravel. So I'll pause for a moment. Okay, so now we come back from the left. And now A is on this statement. So we go down to the right. So it seems like every time we reach a statement, so we're going to pre. So these are pre and post order traversals. There's a video that we went over about the order of traversal, so that's totally not necessary. See that before, so we have a pre, so before we traverse, we print, and after you return from the right, we print. So we can sort of take that intuition and run with it. So before we traverse, we print. So before we traverse C, let's print. Now we traverse left, we come back up from left, go to right, and after we return from the right, we print C again, and then we return back from C, and then we print A. So we print A. And this is the full call. So how can we evaluate this sort of recursion right here? How can we evaluate this recursion? Well, we can use this method called the master method. We're going to build up to it. The general form is as follows. We try to model our function, so t of n. So we're going to use t as our function here. It could be mystery, but we just write t just for short, t of n. And the first thing we're going to write is this a. And what this a means is the amount of recursive calls per stack. So if you remember our stack, we have a stack and we're doing sum, and we're calling sum mystery. We're doing at most 2 calls per stack. So we're doing 2 calls. This is the most amount of work we're going to do recursively. That's going to be times t, so our recursive statement. So our recursive statement is sort of going to have some sort of decrementing feature of n. So some sort of decrementing feature to get to some sort of base case. So again, we have, this can look something like n minus 1, or n divided by 2, and so on. And remember, this is number of recursive calls per stack, sort of, or the number of possible recursive calls per stack. And then how much work are you going to be having of n each sort of iteration? So as we saw, it could be, math. You could be, there could be some sort of iteration happening over here, which would cause there to be like some sort of n work each iteration. If you had to sort things or do some sort of work each iteration, this is going to sort of tell us how much work. So how much work each stack frame. So how much work are we doing in each of those frames? Now, how can we evaluate this? So let's get rid of this. So how can we evaluate this? So let's first model it. Let's put a line through this. And let's go and say, okay, so we have t of n, and t of n is going to be, we have 2 recursive calls, so we have 2 times our t, so 2 times t, and the way we're decrementing is we're saying n minus 1, and then we're going to have plus the amount of work we're having. We're saying theta because it could be big O of 1, but it's also like lower bounded by 1. So if it's both upper bounded and lower bounded, we could just throw in a theta. We can just throw a theta in there. So it is sort of a tight bound. And now we can sort of say, okay, we can substitute this back into our equation. What that'll give us is t to the n minus 1, t to the n minus 1, and that is equal to 2 to the 2, because we're calling this function again. So the more we substitute, the more this is going to increase. The more this is going to increase. So then we go t, and when we plug this back in, when we plug this into the equation, this n here, this input is going here. Remember, this n here, this input was going right before the -1. So again, we're going to take that input, we're going to take that input again. The input is n minus 1, and we're going to put it before our n minus 1, before our n minus 1. And we're going to do plus, theta. Since we already had some sort of theta, we're going to theta plus 1 plus theta, or theta plus 1. So these are going to accumulate, and these are going to accumulate. So if we keep re-substituting in our values, we're going to see, if we keep doing this, we're going to get 2 to the 3, 2 to the 3. We're going to give our t here again, and it is going to be, I don't know why I did that. This is going to be n minus 2 minus 1. So we have n minus 2, have that over here, n minus 2 t plus, and these are going to keep increasing, so we can make this shorter and just say 3 theta of 1, 3 times this theta. And we're going to get a general form from this. This general form, we're going to see that we're going to look at everything that's increasing. We're going to look at everything here that's increasing. So this, and sort of these amount of negative 1s here. We're going to provide a general form. Our general form is going to look like this. So we see that this 2 is incrementing, so 2 to the k. And then we see that this t here, so is having this negative 1 incrementation over and over again. So the general form is going to be k, and it's going to be n minus k. It's going to represent all of these 1s, the accumulation of all those 1s. And then we are going to have plus k theta of 1, So this is our general form. And we're trying to get to this base case. So so the thing we're looking for over here, is when t0, we're looking for t0, and we're looking for when t to the n minus k, let me use the same colors, t to the n minus k is equal to this base case. So what value of k am I going to get for this? We can go ahead and just solve this like any regular equation. And we can see what comes out from this is that we can throw k here, and then we will get that 0, or not 0, there we get that, we get that, we can throw the k to the other side actually, so we can not have a negative k. Throw k to the other side, then we say k is equal to n. So when k is equal to n, we arrive at our base case. So we can take this and plug this back into our original formula. So we can replace every k that we see. We can replace every k that we see with the substituted n. And we can see here that this does work out to t over 0, which t over 0 cancels out to just also being theta of 1, as here we're only doing really like O of 1 work, really, or theta of 1 work. So that's why the base case sort of works out to 1. And then we have here, this stays the same. So now we just have to evaluate the big O of this. I'm just going to keep using the same color now. The big O of this. What is the big O? We're going to be comparing. These are going to combine. So this also gets canceled out. So we're just left with these two. 2 to the n plus, and then this can also cancel out because this can multiply into it. These multiply together. So it's like saying, having that theta there is basically like saying n times 1 times 1. So we just have these two. And we can see that, well, out of the bigger one is this one. So in the end, we're going to have big O of 2 to the n. That is the runtime of this function right here, 2 to the big O of n. So if we were given the Fibonacci sequence, how would you write this as a recurrence relation? How would you write the T formula? What if I were to give a little hints? You can pause the video if you don't want the hints. What if I were to say, if you were to look at these in isolation, what are the runtimes of this? What do you think the runtimes of this are? We have big O of n and big O of n. So we're basically, like within a constant factor, we're essentially just doing n minus 1, n minus 1. So this constant factor of 2 isn't really going to make much of a difference to this overall runtime. So if we were to write this out, if we were to write this recurrence relation out, we can see that, okay, we have this recurrence, so t n minus 1 plus, before we were kind of like multiplying them, we had them right side by side. Here we have them right next to each other. These guys right next to each other. I'm just drawing over them and over them. They're right next to each other, so we're going to put a plus, so t n minus 1. Remember we simplified it to n minus 1. And then we have our work, the amount of work that we're doing, which is basically just some simple math. So it's just going to be every stack frame, we're going to have O of 1 work, or here theta of 1 work. So if we look at this, what does this look like? We can simplify this even further. We can simplify this to 2t n minus 1 plus theta of 1. And we saw this just before, so this means, little pattern recognition here, this means that it's going to be 2 to the n. 2 to the n. Now if I were to change this to 5, what do you think the answer is now? It's going to be 5 to the n. 5 to the n. So when looking at this function, how can we evaluate this function? You see that we're dividing by 2 each time. So if I were to make an array, sort of, and I want to sort this array, this is very characteristic of algorithms that split sort of data into smaller chunks, sort of the divide and conquer mentality. So then do some work on these smaller chunks, and then bring them back together in a whole. Let's bring them back together in some sort of whole. And then here we have this sort of count to n. So we know we're going to do at most big O of n work here. And you might say that, well, we're dividing by 2 each time, so how do you know that we're doing n amount of work? So in our asymptotic notation video, we went over the arithmetic series. So the arithmetic series, so if you see the recurrence or the sort of iteration of I is equal to 1 going to n, so we have some n iteration, and it's nested inside is going to be j is equal to I going to n. Well, this inner loop, the first time it's going to run n times, the second time n minus 1, then n minus 2, and n minus 3, then so on. Even though it's decreasing every time, the entire culmination of the inner for loop, or the entire runtime of this still ends up being O of n squared. So that's sort of the same mentality that we're going to be using here for the amount of work done each iteration. So how can we begin to write this sort of recurrence relation? So we know we have two sort of recurrences right here. So we know that's going to be 2. Then we see we're going to write our recurrence, and it's dividing. So you have here, so it's n divided by 2, n divided by 2. We're going to have plus, we have O of 1 work, so we're just going to do O of n. So we have O of n work every iteration. Now, if we begin to start substituting, we see that n divided by 2, and then we, of course, have to raise it again. And then what's going to happen here? We have to bring the n on top. So we're going to do with our input again and put it on top. And it's going to be dividing by 2. So we're going to see that we're going to have n divided by 2 over 2. Now, we can also write this to be this. So we have a fraction dividing a fraction. So we're going to write the reciprocal and write n over 2 times 1 over 2, which is the same as just saying n over 2 squared. And we're going to keep it that way so we can see a parallel, so we can see some sort of pattern. We're going to keep it unsimplified. So n over 2 squared plus O n plus big O of n. Now our next iteration, we're going to see that we get n over 2 to the 2, which is equal to 2 to the 3, which is multiplied 2, and this ends up being n over 2 to the 3. This ends up being n to 2 over 2 to the 3, and then to simplify it, we'll just do 3 times big O of n. And we can see we can get a general form from this. You can see that this pattern, what do you think this general form is? You see that this sort of general form we get when going down is going to be 2 to the k. So you're sort of getting this sort of relation. So let me erase that. We're going to write, so our general form becomes 2 to the k, and then we get sort of t, and then n over 2 to the k, and then we get plus sort of k again. We get k again. O to the n. And now what we're looking for is our base case. So t, I think this is a typo here, so we're going to have less than. So up here, putting a less than sign. So we're going to have t, we're looking for t is equal to 0 on this sort of general case. When does this happen? When does this happen for this case? Now, it might be hard to get something like this. Usually this is either 1 or something else. But, we can work with constant factors here, and we can just look for an iteration within a constant factor. That's we can look for 1 instead of 0. So we can look for the iteration, minus 1 of or before the base case. It's still going to give us sort of our runtime, so it's within a sort of constant. It's not going to have any difference to our runtime. So we pick this just 1 before the base case, since we can evaluate it. And what we're going to say here is, okay, we're going to try to rewrite this so we can evaluate it as without the parentheses. So how do we get these two to be equal? Well, we can use the identity that sort of x log to the x to the a is that these cancel out and we just get a. These cancel out and we just get a. Let me show you. If we do log base 2 to the k, not k here, log base 2 to the n, these 2's are going to cancel. So this is in the raised. This is raised here. So 2 log 2 to the n is equal to n. These are going to cancel. Those are going to cancel. So what we're left with here is that these cancel. So these cancel, and we get n over n, which is equal to 1. So we're going to say that k, so this is equal to 1 when k is equal to log base 2 to k, not k to n, log base 2 to n. And we're going to plug this back into our formula. So we're going to go here, and place log, we're going to place log base 2 to the n, and then log base 2 to the n, and then log base 2 to the n. And this is going to work out to this one in the middle. So this is going to cancel out to O of 1, since it's basically our base case. We're going to do O of 1 work. Multiplied with the 2, it's just going to be 2. It's going to be 2 log 2 to the n. And then that's also going to cancel out. So we're just going to get here, we're just going to get n. And then, so these cancel out as well. These cancel out as well. Use a different color, so that's noticeable. These cancel out as well. And then we're going to get, plus, let me rewrite it in a different way. We're going to get log base 2 to the n, big O of n. So these are being multiplied with each other. So I can just simplify this and write this as just n. So of course we say that this is going to be the bigger of the two. So this is in all going to be big O of n log n, and we are of base 2. And we see that this is the recurrence relation of this. And you'll often see this in sort of sorting algorithms. See that we're dividing by 2 and doing some sort of n amount of work each iteration. We have come to that same sort of recurrence using this substitute or plug-and-chug method. So this is the master method that we're going to be using in order to solve equations a lot faster. Again, this a here is the same, just this 2. There's going to be 2 here, as it's going to represent the amount of recursive calls that we're making. We're going to now have this b here representing how much is n being subdivided each call. And then we're going to have this d, which is the degree, representing how much work is being represented each sort of stack frame. So right now we have n sort of work, so that means our degree is 1, so d is equal to 1. And if we had sort of theta of 1 work, that means n is being raised to 0, as n raised to 0 is equal to 1. So how are we going to use this? So first, let me write out all the rules. So they're very dependent on the degree. And there's going to be 3 of them I'm going to write out right here. And we can use these rules to sort of get a recurrence relation on the spot. So these are the 3 calls that we're basically going to be looking out for to find our our run times here at the end. We're going to be looking at this d, so we're going to be looking at d, which is going to be our degree here, and our degree here, see that n is just n, so n must have a degree of 1. So degree is equal to 1. Then let's evaluate the log. So we have log, we have 2, so a, we have 2 in the base, and then the base is actually b. So for our b is how many times we're being subdividing, so that's 2, so we're going to put 2 there. And then our a goes on top, and our a is 2, so we're making 2 recursive calls, and that is going to be equal to 1. As in log 2, the 2, what exponent gives us 2? What exponent gives us 2? So that would be 1. So we see that our degree is equal to our log. Our degree is equal to our log, which will give us sort of this relation right here. And if we write that out, so that'll be n log 2 to 2 log n. And this is going to cancel out to 1, which gives us n log n, which we saw before, So here we have these 3 questions, and I formally laid out the sort of master method. And what we're going to do is we're going to work through these, but feel free to pause the video, see if you can figure this out on your own. You can also feel free to try the iterative substitution on all of these, as maybe sometimes you may forget these sort of tidbits, and you may need to come up with it on your own. I find that just knowing these substitutive iteration allows me, when this doesn't really work for me, allows me to get by. But most cases you can just use this sort of master method. Okay, let's go ahead and try to solve these. So we see here that we have 2 recursive calls. So let's go ahead and start plugging in. So for our log, we have 2 recursive calls. And then it's subdivided by 3, so 3 is going to be on the bottom. So log base 3 of 2. So what raised to what gives me 2? Well, we know that if it were what raised to 3, the answer would be 1. So it would be 1. So here, this would be 1. But since this is less than, we know that the exponent here, this exponent must be less than 1. And we see that our degree here must be 1, so our degree is greater than our log. So we see that the recurrence for this is O of n, as our degree is equal to 1. This next one, we see 4 recursive calls. So 4 recursive calls, start plugging it in, subdivided by 3, log is 3. So 3 raised to what? 3 raised to what? 3 raised to what gives us 4? Well, we know this is going to be greater. Than 1. And we have n work, so that means our our degree is less than, so if degree is equal to 1 and our exponent here is greater than 1, then our log is greater, and we see the sort of recurrence of n log 3 over 4 is our sort of big O here. So that's our answer for this. One. Now for this last recurrence, we see 9 calls. So let's do it up here. 9 calls divided by 3 log, and we know this is going to be 2, so we're going to have 2 here. And we have our degree here is also equal to 2. So our degree is equal to the exponent, so our exponent of log 3 to 9. So it gives us this relationship down here. So we're going to get n to, this is going to be 2 log n. That is the relationships. So this last one's going to be sort of almost a trick question. So I'd like you to pause the video and tell me what is the sort of recurrence relation here? What can you gather from this? Okay, let's start writing this out. So we have t of n is equal to, okay, so how many recurrence relationships can we have? So how many together can we have each iteration? We can have at most one. We can have at most one iteration because we have an if statement here, an if statement here, and an else here. So that means only one of these is going to ever sort of happen. So our relationship, our sort of t relationship here is only ever going to have one. So now we can start writing t. So we t. So what are we going to be subdividing here by? Our relationship here is going to be n minus 1, as we see here, this is going to be the largest, this is going to be the lagging sort of weakest link of all of these sort of iterative, sort of recursive calls. And our work, the amount of work we do is sort of, we're not really doing much work on anything here, so it's going to be theta of 1. And we can see that, our general case might end up like 1 to the k, and then k minus n, and then just k. So this is just going to end up being 1. This k is also just going to end up being k. And we know from before this relation just looks sneakily like big O of n. Big O of n. So this is the sort of relationship you kind of have to watch out for. Remember, if there are if statements, only one of these or these stacks within the if statement are actually going to be called. And that is it for the video. If you enjoyed it, don't forget to like and subscribe. This example that you're seeing right here was taken from the open source textbook that is in the description. It is a concise rendering of all these videos and computer science knowledge trying to be crammed into one place. The repositories have topics on computer science, and anybody is willing to contribute. We focus on conciseness and straight to the point, sort of like a definition or a catalog for everything computer science. So I hope you check it out. I hope you like this video. And with that, thank you.